This is Professor Monty, and I wanted to welcome everybody to our Math 11 Calculus class. Let's just jump right into it. Today we're doing sections 1.1 and 1.2. 1.1, as you can see, is called Limits, a numerical and graphical approach. So this first chapter, we're starting with limits and going into the idea of the derivative of a function. But let's jump in first. Let's look at what the definition of a limit is. So let's see, the limit of a function, the limit of f of x as x approaches a is written, the limit as x approaches a of f of x equals L. This means that as the values of x approach a, the corresponding values of f of x approach L. The value L must be a unique real number. And at this point you're thinking, oh good heavens, math just, this absolutely makes no sense to me. Can you speak in English? So let's try to translate this. Let's draw a picture and see what's going on. All right, so I've got my x and y axes here, and say I've got a function that looks like this. And let's call this, we know that's the x-axis, we'll call this a. So this is my function, y equals f of x. Okay, and then we're looking to see what happens. Well, we're saying this, if I go straight up from a, I'm gonna hit the graph about right here. If I extend my y-axis up a little bit, now I go straight across from my y-axis. This is what they're talking about, the value of L. And so the idea goes like this. They're saying, so the limit of f of x, meaning what is f of x approaching? Well, they're saying it's this limiting value L that they're talking about here. The limit of f of x as x approaches a. So the graph is going this way towards A. We don't know which side. It actually has to be from either side. We'll talk about that in just a minute. But as x is approaching that way towards A, the limit of the function as x approaches A of f of x is L. That means as I'm going riding along the curve, so as I'm going this way towards an x value of A, my y value is going up here. And we're saying, well, what value is that getting close to? Well, the closer this x value gets to a, the closer this y value straight up from there, the closer that y value gets to this L up here. And as I come in from the right side, same thing, I'm riding along the curve over here, and it says, well, what's my y value getting close to? Well, it's whatever that value of L happens to be at that point. So if coming in from the left and coming into the right, we're going to the same value. That value L, that is what's referred to as the limit of the function. Now, also notice they said L must be a unique real number. That means you can only be going to one value and it has to be a real number. Notice it doesn't say anything about that point has to exist. And I'll show you what I mean by that. Let's scroll up here a little bit, get some more room to write on. So let's look at a specific example. Say I have my function f of x, we'll just call it 2x plus 1. Well, let's look what's happening there. And we're going to look at this two ways. We're going to look at it, remember the title of this, a numerical and graphical approach. Let's look at it numerically, then we'll go to the curve and see that we're going to get the same answer. What I'm trying to find here is I want the limit of f of x, and let's say as x approaches 3. So we could rewrite this as the limit of 2x plus 1 as x approaches 3. All right, let's see what's happening. Let's draw a table to see what's happening here. So I've got my x values and my y values. Remember, we know y is just the formula 2x plus 1. So whatever I get as an x value, I can just plug in and see what that is. And what I'm really concerned with is what is happening is x getting really close to 3. So we don't care what it is when it's at 0 or 1 or 2, but let's get close to 3. Picture-wise, remember, we're saying what's happening right up here when I didn't mean to erase all that stuff. What's happening right up there? Let's just draw something back up through there. We know it went up We don't need those colors, we'll use that. We know the graph went up through here, and so that was my point of interest right there. But what's happening really close right here, right? We're coming in from the curve both directions. All right, so let's plug in as some x value, something really close to 3. Let's start with, say, 3.1. So at 3.1, now all I'm doing is I'm plugging that in for x. So I'm just saying, oh, 2 times 3.1 plus 1. Well, 6.2 plus 1 is 7.2. But now let's get even closer than that. Let's do this. Let's back up because I want to see it coming from values below and then values above. So I'm going to erase that. We know the idea of what we're doing now. So let me just erase that value, this value. We're still going to plug those in, but let's look at it from the two sides. So let's go less than 3. So let's say maybe 2.9. When I plug that one in, again, I'm just plugging it in. 2 times 2.9 is 5.8 plus 1, 6.8. Let's make it even closer, 2.99. When I do that, I get 6.98. And then when I plug in 2.999, I get 6.998. And so notice what's happening here. X is approaching 3. Now we've even got a term for this. Since we're to the left of 3, we'd put a little negative right there saying it's approaching 3 from the left. And in fact, we would write it as the limit as x approaches 3 from the left of 2x plus 1. Now we see as I'm getting closer and closer, my y value is getting closer and closer to 6. Oops, that's not a 6, it's a 7. Y is getting closer and closer to 7. 6.8, 6.98, 6.998. It's getting really, really close to 7. As x gets really close to 3, y gets really close to 7. Well, that's my limit as x approaches 3 from the left-hand side. Let's see what happens from the right-hand side. So let's go back and I'll pinch into it. So let's say we're at 3.1. If I plug that in, I'm going to get 7.2. But if I plug in 3.01, so now I'm to the right of 3, but I'm getting really close to 3. That's actually 7.02. And then if I do 3.001, that's 7.002. And again, I'm just plugging them into the formula, y equals 2x plus 1, whatever my x value is. But notice this way, now x is approaching 3, but it's above 3, so this is approaching 3 from the right, so we just write it that way. Again, though, notice the y values are still approaching 7, same 7. So we would write that the limit as x approaches 3 from the right of 2x plus 1 is also equal to 7. The first one we do, it's called the left-handed limit. Left-hand limit. And then the other one's the right-hand limit. If those both exist and they're the same thing, then the limit itself exists. So we would write the limit as x approaches 3 of 2x plus 1. Since I haven't written from the left or the right, it implies that it's the two-sided and that they're equal to each other. So that limit is equal to 7, and that's my answer. Now we had to go through a lot to get there. We're going to see in the next section an easier way of getting this particular limit, but we found the limit was 7. Let's see how that relates to the graph. So now if I graph this, so that was numerically how we would find a limit at a certain point. Okay, now what if we do it graphically? And again, we're still finding the limit as x approaches 3 of 2x plus 1. Now, that graph, y equals 2x plus 1, just a line. Let's plot a couple points so that we know where to graph it. I know at when x is 0, y is 1. When x is 1, we plug that in. 2 times 1 is 2 plus 1 is 3. So I've got a line that goes through those 2 points. So let's go ahead and graph that. I only care about the first quadrant, so I'm going to make that larger. But I know I go through 0, 1, and then I'm even going to make that scale even a little bit bigger. So let's erase all of that. All right, so let's see. So let's go up to, because we're going out to x equals 3. 1, 2, 3. So there's 10. 1, 2, 3, 4. That's not a very good 4. 5, 6, 7, 8, 9, 10. 1, 2, 3, 4, 5. We'll go out to 5 this way. That's plenty. Okay, I know I went through 0, 1. That's here. And I know I went through 1, 3. That's here. So let's just draw that line. Something like this. But the question is, what's happening as x approaches 3? Well, let's see. We'll see how good my scale is. So what I'm doing is I'm going up from 3 up to the curve, and I'm following that straight across. It's about there. And I'm saying, okay, graphically, what's happening? Well, this is the point. If we see what I just did right there, x is 3, y is 7. So it's the point 3, 7. Remember, x is getting really close to 3 from the left. Well, following along the curve, if I'm straight up here, it's starting here, but as x is going there, the y value is going up along the curve this way. And the closer and closer x gets to 3, the closer and closer y gets to 7. So I see from here, since this y value is getting really close to 7, as its x value is getting close to 3, I would say again, oh, the limit as x approaches 3 from the left of my 2x plus 1 is 7. But the same thing happens from the right. We'll use another color. As I'm coming in from the right, we're coming down the curve this way. And as I get closer to x equals 3, my curve's getting closer and closer to y equals 7. So again, same thing. Limit as x approaches 3 from the right of 2x plus 1 is also 7. Since they're the same, then that tells me the limit does exist. The limit of 2x plus 1 as x approaches 3, again, that's the two-sided limit, is equal to 7. There's my answer. And it concurs with what we did when we plugged in points. It's a lot easier to see it on the picture than it would have been on what we did before. Now, here's what's really kind of interesting, if you ask me. We're talking about a limit. That 0.37 doesn't have to exist. So let's draw another one of those. Same curve. Y equals 2x plus 1. Well, it's coming from there. But let's say my domain, no, we're not going to write it that way. My domain is going to be everything except, so we'll just write here, x not equal to 3. So I've got that function, y equals 2x plus 3, but x isn't defined at 3. Y equals 2x plus 1, x not equal to 3. So if I draw this curve, it's still the same line as I had before. I still go through 0, 1. But at that 0.37, that point doesn't exist. It's an open, it's just a hole. So the graph exists on both sides, but it doesn't exist at that point. Now, here's the thing, though. If I'm looking at the limit as x approaches 3 from the left of 2x plus 1, again, I'm still coming in. My x value is getting closer and closer this way. Ugh. my x is getting closer and closer this way to 3. And so on the curve, I'm going this way. I'm getting closer and closer. Notice as this x gets closer to 3, that's still getting close to 7. Even though that point doesn't exist at 3, 7, the limit does exist. The point doesn't have to be there for the limit to exist. Because remember with the definition of the limit, it says as x is approaching that number. It doesn't say it ever gets there. As x gets close to that number, 3 in this case, what's y getting close to? Well, the y value is getting close to 7. Doesn't reach the point. That's not what a limit is. A limit doesn't have to reach the point. The limit just says as I get really close. Similarly, as I come in from the right side towards 3, my graph's coming down this way, getting closer and closer to y equals 7. So I would write that limit as x approaches 3 from the right of 2x plus 1 is also equal to 7. So this one was the same graph as before, except it had a hole at that point of interest, x equals 3. But the limit still exists. Notice if I went up here and I said, what is, say we called this f of x, and I said find f of 3, I would just plug that in. Oh, 2 times 3 plus 1, that's 7. And I see on the graph, yeah, that's the point. When x is 3, y is 7. But down here, that point doesn't exist. So now if this is my f of x, and I said find f of 3, well, remember what f of 3 means. 3 means when x equals 3. What is y? That's the question that's asking. But you know what? It's an empty hole right there. 3 is not in our domain. So this is going to be undefined. So this one, we don't have an f of 3 because there's an empty hole there. Didn't change the limit though. That's the key here. The limit still exists, even though the function value does not. Okay, so that's the basic idea of what we're doing there. What I want to do is I want to jump into a couple examples graphically where we can look at these two-sided limits. So let's raise this up a little bit, get that a little bit out of our way. And I'm going to go pull up another picture for us. So here's a problem. I guess I didn't need to pull that whole thing up. We'll just copy this. And we'll paste it in. All right, so let's paste this right here. All right, so here's a problem out of the book. And we see it's problems 23 and 24. And so it says, consider the function. So they give us the function. It's one of those piecewise defined functions, but they're giving us the picture. And they say from the picture, determine what these limits are. So notice, let's look at 23. It says, let's look starting here, part A. We'll write that down. So it says, let's see, we'll do 23A. It says find the limit as x approaches 4. Notice that minus doesn't mean negative 4, it means 4 from the left of g of x. All right, well, let's see what we're doing. We're going towards x equals 4. So graphically, we're coming in this way towards x equals 4. From the left, well, the function value is right here. So as x is getting close to 4, we're coming along the curve that way, and we're getting really close to y equals -1. B says, well, what happens when you take the limit as x approaches 4, but coming in from the right-hand side, oops, make that a little bit low, of g of x. Well, let's erase that. We still have that same point. Well, what we're saying now is we're coming in from the right. So X is coming in this way. That means we're coming up this way on the curve. And we're getting really close to -1 as our Y value again. Remember, those function values, those are Y values. And then C just says, well, what is the limit as X approaches 4 of G of X? Well, since those are equal, that's what our value is. If those weren't equal or one of them did not exist, we'd have to say the limit does not exist. Okay, so that was problem 23. Problem 24 uses the same picture, but now we're looking over at -2. So let's move this up just a little bit. Keep that picture in mind. So problem 24, I'll just write it right here. So 24a, find the limit of G of X as X approaches -2 from the left. All right, so this time on the curve, let's get rid of all that. This time we're saying, okay, well, there's -2. We're coming in towards -2. Well, on the curve, I'm coming in towards this. Well, and as X gets closer and closer to -2, Y is getting closer and closer to 4. So that value is a 4. Then the problem says on part B, it says, well, look at that same limit, but this time X is going to approach -2 from the right side. Well, coming in from the right side, I'm coming in up here. I'm not approaching 4 anymore. This time I'm approaching 2. So both of the two-sided limits exist, but they're not equal to each other. So in part C, when it says, well, find the limit of G of X as X approaches 2, we have to say does not exist. A lot of times, let me box that. The reason is because the two-sided limits are not equal. A lot of times they'll just write DNE for does not exist. Now, I want to add something to this. If they said, well, what is, we'll make this up as D. If they said, well, what is G of -2? Oh, G of -2, that means when X is -2, what is the Y value? Well, when X is -2, let's erase all these things so that we don't get confused. When X is -2, the Y value is where the solid dot is. Oh, the Y value is 2. So that value did exist, it was 2. It wasn't 4 because we have an open circle there. If I look up here and we add a part D to this and we say find, oops, it's not F, it's G. Find G of -2. It's also -1 because when G is -2, oops, it wasn't -2, it was 4, wasn't it? When G was 4, Y was -1. That was actually a dot on the curve. So we could find G of 4 and G of -2, even though the limit at 4 existed, but the limit at -2 did not exist. Remember, a limit doesn't mean the point is there. It just talks about whether or not it exists. Okay, so almost done with this section. I have one more example that I did want to show you. So let's move this up and pretty much out of the way. Let me pull another problem out that I'd gotten from here. This one. Let's see, we'll copy that. We'll go back into our problem and we'll paste it right here. Okay. So we don't need to spend as much time on this because we've already seen how it works. We just need some more examples. So this one gives us a bunch of different things. So let's see. So first off, they say find the limit of f of x as x approaches -3. Well, here's -3. Well, I've got a problem because as I come in from the left, I'm going towards 4. right? That's my -3. That's not my -3. I'm looking at the wrong place. All right, let's try that again. So -3, if I go up from -3, it's right there. Well, as I come in from the left, I'm going towards that y value, which is 5. As I come in from the right, I'm also going towards 5. So this does exist. That's a 5. All right, let's erase that. The next one, what about -2? Well, let's erase those dots also. Well, at -2, oh, here's an issue, because now it's coming in here. So as I come in from the left, I'm getting really close, right? That's straight up from there. I'm getting real close to 4. But as I come in from the right, I'm getting real close to 2. So the limit from the left is 4. The limit from the right is 2. Not the same number. So here we would write does not exist, because we're going to different numbers. All right, let's erase all that. What about as we go towards 4? Well, notice 4, ooh, we haven't seen this before, but at 4, we're going straight up there. There's an empty hole right there. Well, let's see what happens. Coming in from the left, we're going towards the hole, which is at a height of 2. Coming in from the right, we're also coming to that same place, a height of 2. That's my limit. My limit is 2, because it doesn't matter if you come in from the left or the right, you're going towards y equals 2 either way. Here's one where it's just a hole. It doesn't have to be a jump. So again, the two-sided limits exist here, even though the point does not exist. All right, let's try some more. Let's see, -2 from the left. Okay, -2 from the left. We already talked about that. -2 from the left, that's here. We're coming in this way. Oh, I'm going towards 4. What about -2? Oh, that was -2 from the right, wasn't it? So -2 from the right, I'm actually going towards 2. Oops. -2 from the left, that's where I was going towards 4. All right, what about the limit as x approaches 2? Well, x approaches 2 is here. That's just going to this y value. They're coming from the left or coming to the right. I'm still going to the y value of 4. So that's a 4. X approaches -5. Well, that's over here. Well, that's coming in from this side or this side. I'm going towards y equals 0. And the limit as x approaches 6. Again, coming in from the left or the right, I'm going towards y equals 0. So make sure that those make sense to you. That's going to be the end of this section, and I'm going to jump right into the next section. But one of the good parts about having this on video is you can rewind and go back and cover up the answers and see if you can do it yourself. Okay, so let's jump into my next section. So we're doing 1.2, algebraic limits and continuity. So now what we're doing, we'll refer back to some of those graphs. In fact, I don't need to pull those same graphs back. We could look back. You may want to look back later and see which ones are continuous. We'll talk about that soon. But here's another way of looking at graphs. Now, algebraic limits. First one that I want to show is, you want the black pen here. The limit of a constant is the constant. Let me show you a function that I'm talking about, and we'll even show you the picture to show you what I mean. So for example, say I've got the limit as x approaches 2 of 5. Notice there's no place to plug in that 2. My function is y equals 5. It doesn't care if x is 2 or 9 or 17 or -3. The value of the function is still 5. This is always 5. It's whatever the function value is. I'll show you the picture. There's my x and y axes. I've got the line y equals 5, or f of x equals 5 if you want. But all that is It's a horizontal line up here at 5. That's my line y equals 5. Well, if I go to x equals 2 and go straight up, you know what the y value is? Yep, it's 5. So that's the 0.25. The limit exists because if I come in from the left, I'm going towards y equals 5. If I come in from the right, I'm going towards y equals 5. So that's my limit. The x value didn't matter. It was just if the function value is always 5, no matter what x is getting close to, the function value is still 5. So that's all that is. And it's an easy concept to understand. But if you just look at this, you may say, I don't know. But if you understand what it's asking, then it's a pretty straightforward problem. All right, so we've got that idea of the limit of a constant. Now what I want to show you, though, is what happens. This is actually problem 9 out of the book. It says find the limit as x approaches 1 of 3x plus 2. Now this brings up the next idea. If you've got an x value in there, you don't have just a constant like we did in the previous problem. All we do is we plug in the x value into the function. If it gives you a real number, that's the limit. So I just plug that x in and I say, oh, that's 3 times 1 plus 2, which is just 3 plus 2, it's 5. Yeah, that's actually the limit. So if you plug it in and you get a real number, that real number is your limit. That seemed a little too quick and straightforward. Let's look at problem 17. It says find the limit as x approaches 3 of x squared minus 8 divided by x minus 2. You know what we do here? We plug in the 3 wherever there's an x. So I'm plugging in the 3 squared minus 8 over 3 minus 2. Well, 9 minus 8 over 1. Doesn't look like a very good minus, does it? 9 minus 8 over 1 is just 1 over 1. It's 1. Now, the reason both of these work, I could graph both of those functions. On problem 9, I can graph y equals 3x plus 2, the line. But that line goes through the point, x is 1, y is 5. It's just a point on the graph. Similarly, the point x is 3, y is 1, 3 comma 1 is a point on the graph of y equals x squared minus 8 over x minus 2. So if I plug the x value in and I get a real number value, that's my limit because it's just a point on the graph. All right, so those are pretty easy and straightforward. That's the first thing I want you to do whenever you're looking at one of these and you try to figure it out. But look at problem 19. Now we got a little problem. Limit as x approaches 5. Looks very similar to what we just did. The numerator x squared minus 25, the denominator x minus 5. We see that, we just plug in the values. 5 squared minus 25 over 5 minus 5. Well, the top 25 minus 25 is 0. The bottom 5 minus 5 is 0. And we have a problem. 1 over 1 was okay, that's just equal to 1. But 0 over 0 is not equal to 1. It's not equal to 0. It's undefined because you can't have a denominator of 0. But here's what happens. If both the top and the bottom are 0, whatever's making the bottom go to 0 also made the top go to 0. This doesn't mean the 0 over 0 doesn't mean that the limit doesn't exist. It just means there's no point on the graph at x equals 5. So no y value at x equals 5. Again, that doesn't mean the limit doesn't exist. It just means there's no point there. And we know that, remember, if you were to graph this x squared minus 25 over x minus 5, there's a vertical asymptote at x equals 5 because that's what makes the denominator go to 0. The graph of a function can't cross a vertical asymptote because there's no point in the domain there. So here's what we do. we say, oh, you know that x squared minus 25, I can actually factor that out. That's the difference of two squares. The top is x minus 5 times x plus 5. And again, the order doesn't matter. If you did the x plus 5 first, that's fine. Now the x minus 5s cancel out. And I just have the limit as x approaches 5 of x plus 5. Now I can plug in the 5. And I get 5 plus 5, which is 10. That's my limit. So this is another case. If I were to graph this, this is a line with a hole in it, is what this is. The hole is that x is 5, y is 10. The point doesn't exist, it's a hole. But the limit exists. So that's typically what's going to happen if you get something of the form 0 over 0. All right. Now, let's jump down. I want to show you a couple as x go to infinity. And these are going to be straight from what you did when you were graphing rational functions. I'm not going to spend a huge amount of time on these. There's 3 examples. The first one's 31. There's 3 different possibilities here. So it's the limit as x goes to infinity. And then they give us a rational function, 5x minus 2 over 4x plus 1. And so you've probably seen this in intermediate algebra. You've probably seen it in college algebra, graphing the rational functions. The limit as x goes to infinity, that's actually horizontal asymptotes. So if you remember how to do horizontal asymptotes, it's the same thing. And if you remember how to do those, whatever your answer was for the horizontal asymptote, you can just write that down. But here's what happens. When x goes to infinity, we call that the largest power dominates. So I can ignore this minus 2 and this plus 1. We'll just cross them out that way. And really, because as x goes to infinity, the minus 2 is so inconsequential. So if I look at this, I can really say as x approaches infinity, what's 5x over 4x? Now, by the way, that plus 1, for instance, on the bottom, inconsequential because say I put in a billion, 4 billion plus 1, that plus 1 really isn't a big deal. If you meet somebody that has $4 billion and you say, hey, will you do me a favor? And they're like, no. You're like, I'll give you $1. Like, I've already got $4 billion. That extra dollar, I don't care. That's why we say as x goes to infinity, as x gets big enough, that plus 1 or the minus 2 on top doesn't matter. All right, so I can just look at my highest powers. Well, since those are the same powers, the x's cancel out. Now I've got the limit as x approaches infinity of 5/4. That's 5/4 is a constant. Remember, the limit of a constant is just the constant. So I get 5/4 as my answer. That's always going to happen if the powers of x on the top and the bottom are the same. If the highest power on the top and the highest power on the bottom are the same, you're just going to reduce down to some constant. Well, what happens on a problem like 37, limit as x approaches infinity, 8x plus 1 is the top, x squared is the bottom. Now it's something different. Notice the power on the bottom is bigger. Always the same thing is going to happen here. Again, this plus 1 doesn't really matter. Now, in general, I can't cross out those things that aren't the highest power except when x is going to infinity. If x is going to some number, that plus 1 matters. But as x goes to infinity, it does not. So what this problem becomes is the limit as x approaches infinity of 8x over x squared. And now this x on the top cancels with one of these. So now it becomes limit as x approaches infinity of 8 over x. Now as x gets really big and it's the denominator, the fraction, you may know what it does. Let me show you real quickly what's going to happen. Let's do x and then 8 over x. Well, when x is, say, 1, 8 over 1 is just 8. But if x is 10, 8 over 10 is 0.8. And at 100, 0.08. And at 1,000, 0.008. So as x is approaching infinity, the y value is approaching 0. It's getting smaller and smaller. That's what's going to happen anytime the power on the bottom is bigger. Means the bottom is going to grow faster, means the fraction shrinks down to 0. Okay, so one more example, problem 40, and then we'll just look at a couple pictures, talk about one more thing. Problem 40, limit as x approaches infinity. This time what they give us, the numerator is x to the 5th, the denominator x cubed plus 4x plus 10. Again, let's kind of shortcut this a little. The stuff that's not the highest power doesn't matter. If I look at x to the 5th over x to the 3rd, 3 of these cancel 3 of these, I just get a 2. So really what my problem is the limit as x approaches infinity of x squared. Well, as x gets bigger and bigger, x squared gets bigger and bigger. This goes to infinity. Oftentimes they'll say does not exist because it's not a real number. Some authors will say, hey, you know what, put infinity. If it's infinity or negative infinity, put that. If the two-sided limit, there's no two-sided here because we're just going off to the right. If the two-sided limit of something are one's positive infinity, one's negative infinity, then you would say does not exist. But in this case, you can do it either way. You'll have to check to see on my math lab if they do it does not exist or an infinity. Again, some authors do it one way, some authors do it the other. But here's the idea. As x goes to infinity, all you do is you look at the highest powers. If the highest power on the top and the bottom, like on problem 31, are the same, you're just going to reduce and you're just going to end up getting what those reduce to, 5/4. If the power on the bottom is bigger than the power on top, it's always going to go to 0. And if the power on the top is bigger than the bottom, it's always going off to infinity. So those are the 3 different options. And again, that's what we would do with the horizontal asymptotes. For this graph on 31, there's a horizontal asymptote at y equals 5/4. 37, a horizontal asymptote at y equals 0. And on 40, there's no horizontal asymptote. The graph off to the right just goes up, 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 up without bound. Okay, one last idea in this section. It's the idea of continuity. So let me post the definition for you. There it is, continuity. So let's copy that, we'll paste that in here. All right, so a function is continuous at x equals a if f of a exists. That means there is a y value there. The limit exists. Remember, that's the two-sided limit, and those are equal to each other. So if the y value is there, the limit is there, and they're equal to each other, then the graph is continuous there. Now, and that's a very technical definition. If you're a math major, you would need to know the technical definition. For our purposes, really, we could say this. The graph is continuous. Oops, move that up so I don't write down on the bottom. Continuous at x equals a if we can draw the graph through, we'll just say x equals a. Whatever point that is, it's a comma something. Here, let's say this. Since we're using f of x, we'll just call it through the point A, comma, f of A without picking up our pen. What does that mean? That means there's no hole or jump at that point. And so I'll just show you examples, talk about what we're talking about. I will tell you in the online homework, which would mean fair game on the online exam, what you have to realize is that they may ask you, oh, why isn't it continuous at this point? And then the answer would be, oh, the limit doesn't exist there, or the function value doesn't exist there, or they're not equal to each other. So we'll look at some pictures to see what this is. But let's look again at this definition. So the function value exists. That means there's a y value for that x. The limit exists at that x, and they're equal to each other. And they're saying, you know, if any of these aren't true, it's discontinuous or it has a discontinuity. They're just using formal language to make themselves sound smart. But let me look at an example. It's some different pictures, and we're just going to talk about what makes it continuous or not. So as you can see here, there's 5 different pictures that we're going to do. Let's post that on there. And here it is. Okay. So let's look at these. Determine whether each of the functions shown is continuous over -6 to 6. So they're giving us the graph from -6 to 6. So let's just start talking about these. And here we have a break. There's a big jump in this first one right here. So the graph's going, and this would be a problem because the two-sided limits do not equal. If I come in from the left, I'm going here. If I come in from the right, I'm going here. Well, that's different places. This limit does not exist. So let's say no. Oops. No. Determine if each of the functions is continuous. No. So we'll talk about over here why. 47. Limit of f of x. Well, that's a g of x. Limit of g of x as x approaches -2 does not exist. Okay. That's why that was no. Well, let's look at 48. Again, there's a jump. So I would say no. Same reason. 48. Limit of f of x as x approaches 1 does not exist. So it's not continuous. What about 49? Ooh, notice on 49, we go here, we come here, we come up here, we go. I was able to draw all that entire function without picking up my pen. So you know what? That one's a yes. That is continuous over everything. Now notice, look back at 47. We said this isn't continuous over the interval, but what we have to realize is if I'm going through here, the function's continuous here and 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 here, not there. So it's continuous from -6 to -2. And again, from -2 to 6, it's just not continuous at -2. If I said, is the graph continuous at 1? You'd say, oh yeah, at 1 right here. Yeah, I can go draw right through there. It's continuous at 1. It's continuous at 2. It's continuous at 3, 4, 5. Just not continuous at -2. So the question, these yes and no's means, is it continuous on the whole interval? If it's not at any one point in the interval, then we would say no. Now this next one, notice right here, there's a hole, 150. So if I'm trying to draw this and I'm coming through and I'm drawing on my curve and I say, wait, there's a hole. I have to jump over here and now I can go continuous, 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 but it wasn't continuous right here. So because there's that little hole, we have to say no. So let's see. So 49, we just said yes, but 50, why not? The limit exists. That limit as x approaches -1 think that was a -1. Let's erase all this. Yeah, the limit as x approaches -1 did exist. It was 2. The function value didn't exist, though. So if I tried to do f of -1, there's no value there. So this doesn't exist because f of -1 does not exist. And then if we look down at this last one, 51, the limit doesn't exist at -2. They're both going up to infinity, so we may say the limit's infinity, but it's not a real number. So here, the limit of t of x, on 50, I called that f, but that's actually a k, isn't it? Let's clean that up for correctness forms. So the limit of t of x as x approaches -2, let's just say not a real number. Again, I don't know if our author says does not exist or infinity, but it's not a real number. Okay, so now let me give you a quick example of what they were talking about before when they talked about those, everything equaling each other. Let's look at a point that exists. Say on problem 50, this k of x, right here. It goes through the point, let's not use 0. That might be a little confusing. Let's use, well, at 2, it goes through -1. So this goes through the point 2, -1. So on 50, we'll say on 50, number 50. Well, it's just horrible. On number 50, okay. So now when I look at this, I can say the limit of k of x as x approaches 2 is equal to 1. Because if I come in from the left, I'm going towards -1. As I come in from left, I'm going to -1. As I come in from the right, I'm going to -1. So that limit exists. The two-sided limit exists. Also, if I say, well, what is, so let's see, here was part A. Part B would say k of 2. Well, that's saying when x is 2, what is y? Oh, that's also -1. So when x was -2, that was my y value. And since those are the same, we would say yes, k of x is continuous. Now, up here we said no at -1, but remember it's continuous everywhere except -1. So k of x is continuous at x equals 2. And x equals 2.5, and x equals 3, and x equals 0, just not at x equals -1. So we could do it like we did on problem 50 for any of the points where the point exists on the curve, because your pen would go straight through that point if you were graphing it. Okay, that's the end of the lesson today. I know it was kind of long, kind of our introduction into limits, but we did 2 sections. Some of the days we'll do 2 sections, some of the days we'll only do 1 section. But if you have any questions about this, feel free to ask me during the live session, and try the problems from 1.1 and 1.2 on your practice exercises, the practice for exam 1 in my math lab. All right, well, best of luck to you. Hang in there, and you can do this.